When we've been solving acceleration problems, every time there's a displacement part, we've always got an exponential, okay? And you can absolutely always use the equations that we already have. But there are circumstances where it's easier to do the displacement a different way, okay? And I want to show you what that is. I'm going to have a velocity versus time graph, okay? I'll have something, I don't know, starting at 50 meters per second. I'm going to leave out the units. Going down like this. Okay, what's really important here, going down to 10 meters per second. What's really important is that this is constant acceleration. I can't use this little, I'm not even going to call it a trick. I can't use this approach unless it's constant acceleration. So if this is bending in any way, I'm out of luck. Can't use it. Constant acceleration. But remember, constant acceleration is what we're doing all our equations with. Our delta x equals v0 vit plus 1/2 at squared. All those equations are constant acceleration. A is one number. Never changes. Okay? Velocity changes all over the place. But the acceleration is one number. So this has one slope. If that's the case, then geometry would tell us that the average would be the average of the initial and the final. If I'm averaging your height and my height, we add them together and divide by 2. So V average is going to be VI plus VF divided by 2. Okay, it's the average of those two. Why is that useful? Because look what equation we can now use. Remember, we couldn't use this because VI doesn't have that symbol. VF doesn't have that symbol. This is an average velocity. It doesn't belong with those other ones. Delta x over t. Look what I can do now is if I can average those and I have the time, I can find the displacement. Or if I have the displacement, I can find the time. Okay. Now there's no free lunch, they say. If you're taking in acceleration any equation that has displacement in it is an exponential, has an exponential. You can't replace an exponential with a linear, right? But so we're not going to be able to replace that with something you can do in your head. But if we do two things, if we do two little linear equations, then we can replace that equation. It makes it easier. So one of them has to do with this phenomenon. Velocity is linear. It's easy to figure out. Okay? If I told you I drop a ball, you know after 1 second, it's going to be going 10 meters per second. After 2 seconds, it's going 20, and so forth. So you can do velocity in your head. I want you to be able to do velocity in your head. So that's one equation. This is the other equation. So let me show you what I mean. I throw a ball up at 40 meters per second. I'm just going to write down the equations right now. The variables right now. Okay? And I'm going to want to find out how far away it is, delta x, I'll call it delta y equals question mark, after 4 seconds. Okay? And I know that the acceleration is -10 meters per second squared. Okay, so the first thing I have to do is I have to say, okay, I could use delta y equals vit plus 1/2 at squared. Let me do that right now just to show you that this works. Vit plus 1/2 at squared. So this is one way of doing it. Okay? And in fact, in my class, in a checkpoint, I will have you do a problem with free fall. I'll have you solve it this way just so you know what the answer is. So then when you're doing it this way, you're comfortable that you got the right answer. So let me try that. Okay? On a test, you could do it this way as long as you're confident and you do it right. Don't do it wrong. Delta y equals VI 40 times 4 plus 1/2 times -10 times 4 squared. This is 160. This is minus 80. And this ends up being 80 meters. Okay? So that's my actual answer. That's one way to do it. I can't do this in my head. So I'm going to show you a little trick. The little trick, I'm going to erase it, but I'll write 80. Remember that the answer was 80 meters. It's 80 meters higher than it was. Okay? So I kind of wished I'd done a different time. That's not really what I wanted. But, okay, so now let's talk about the velocity. The velocity was 40 meters per second when it took off. After 1 second, that changes by 10. 30 gets slower. 20 after 2 seconds. 10 meters per second after 3 seconds. 0. So actually, at this time, it's up at the top. My final velocity is 0. Okay, that's why I kind of wish I'd used 5. I wanted it coming back down again. It works even if I did it for a longer time. Okay, now look at what I've got, VI and VF. The average velocity is going to be VI plus VF. Don't confuse it with the acceleration equation. VI plus VF divided by 2. It's the average of the two of them. 40 plus 0 divided by 2 is 20. Average velocity was 20. Hey, guess what? Average velocity is displacement over time. So 20 equals displacement over 4. Displacement is, I should have written y, but 80 meters per second. 80 meters. Okay, so why did I go through all that? Well, if I do all the V0t or VIT and 1/2 AT squared, I don't have to do all this. But here's the advantage of this. I did this part in my head, right? It changed by 10 every second. I did that part in my head. So that was really fast for me. And then I did this, 40 plus 0 divided by 2, 20 in my head. And then I said average velocity times time equals displacement. I did that in my head, okay? There are going to be problems that are a little harder that maybe you don't want to do that. But that's one easy way to do it. Now let me show you another thing. And this is something you're going to be doing in a moment on a checkpoint. How about after 5 seconds? Let me get rid of this. I can't do it with my finger. Let me get rid of this. So after 5 seconds, well, after 4 seconds, it was up at the top. After 5 seconds, it's coming down. The velocity would be -10. Okay, the average of those two, 40 plus -10, is 30 divided by 2. The average velocity is 15 meters per second. Notice that average is smaller than it was before, right? It's starting to come down. Average velocity equals displacement times time. Equals displacement over time. So displacement, delta y, is going to be average velocity times time equals 15 times 5 equals 75 meters. Remember that last one was 80. It's coming down. So it's 5 meters below where it was. So it's really easy for me to do this once I get the hang of it. But I got to be very, very careful. It has to be constant acceleration. I've got to be really confident averaging two numbers. I do need to understand how velocity works, how in free fall only it's changing by 10 meters per second every second. If I had something going down a ramp with an acceleration of 2 meters per second squared, that velocity would be changing by 2. I just have to repeatedly add or subtract 2. So I can do velocities in my head. I can average those two. Don't have to do it in your head. You can do it on a calculator. And then I can use it with that really easy equation to find the total displacement. What you're going to find is on the checkpoint, it's actually a lot easier after the first couple of data points to do it this way. Now, here's the big warning. Oh, there's one other thing I'll say. It's possible to set up a problem where you have to go the other direction. So if I gave you the final velocity and the acceleration and the time and the displacement, I shouldn't say it. If I gave you the time, the displacement, and the final velocity, there's no one equation that works for that. So what you'd have to do is delta x over t gives you the average. And if you know one of these, you'll be able to find the other because they have to average out to that number. I'm not going to do that example for you right now. It doesn't come up that much, okay? But I do want to say one more thing. And this is the warning. Here's the angry face. Warning. Don't use this equation unless you're really comfortable with all the other solve method equations, with all the ones that we've learned before. Okay? If you're not good at those, don't jump into this. Okay? This is only for people who have a really strong understanding of those other equations and can very easily remember this and then apply it there. But if you use this and you plug in the wrong thing, if you plug in VI in there, it's going to be wrong. It's a disaster. If you're going to plug VF in there, it's wrong. It's a disaster. It's only if you find the average velocity. So keep track of your VI and your VF and your average velocity. Don't confuse those. There's even another one we use sometimes, right? Delta V, VF minus VI. Don't confuse this, positive and negative, because that's with delta V. We don't want that. So if you're very, very careful and you find this method to be faster for you, you can absolutely use it on a test or a quiz. It saves a lot of time.